Welcome to this Aspen Plus tutorial on reactors, and today we'll be looking at a set of reactions or reaction group different from what we saw previously. And previously we looked at the power law models or reactions that followed the power law kinetics. And today we want to take a look at the Langmuir, Hinshenwood, Haugen-Watson reactions in Aspen Plus, and how to specify such reactions or kinetics in Aspen Plus. Not all reaction systems or reacting systems are well represented by power law kinetics, and some are more complicated, especially when you have a catalyst, a heterogeneous catalyst in the reactor. Those kind of reactions normally are better represented using the Langmuir model, right? So we'll see how to model those in Aspen Plus as well. A quick revision of our units, the importance of units in uh, simulating reactors. Right? So we would dive or delve quickly into solving a problem, and when we get to that point, the necessary steps or modifications that are necessary will be depicted. The problem looks at hydro demethylation of toluene, right, in a packed bed reactor, and these are the conditions, right, for the feed. So we would quickly go into Aspen and then start with our component specification. As so we have toluene, methane, benzene, hydrogen, and inert component, which is nitrogen gas system. We go on to choose our property method. Here we use SRK, solver, and then we set this to steam and BS. We don't use the steam table correlations. And you can head to our simulation environment, to the model palette, reactors, PBR system configuration, connect our feed and product streams. Right. When we come back to our problem, first the units are standardized. Then we would look at this a bit later. But then the flow rate, we were given the flow of toluene, its percentage. So based on that, we're able to calculate the total flow rate for the fraction. So we can specify a material stream, specify them as such, and that's for the material stream. We go on to our block. We are operating isothermally to specify temperature. We want to keep it constant at the inlet, 640 degrees Celsius. The configuration, they have a length of 0.75 meters, that diameter for our reactions. So we create a new reaction set as we know, and that's where things start to change. So over here, instead of a power law model, we choose the LHHW set. Then we can add our reaction. So we have toluene and hydrogen. So this is where things really start to change, right? So if we go back to general form. Right, you see, so this expression here depicts the general form of the Langmuir model, and so it usually has the first factor is the kinetic factor that multiplies based on the Arrhenius relation or equation. Then there's a driving force term, and then an absorption term. Right? So the kinetic factor, which is the first term, you see, is Arrhenius dependent, temperature dependent. Then the driving force term, depending on whether it's a reversible or irreversible reaction, one of these might be or might not be present. Right? We have the absorption term, which is some sum in products of absorptive constant and concentration terms. Now, again, the terms for concentration could be partial pressure, fraction concentration, right? So depending on the system, the system or the type of concentration being used, the units will also vary or differ. So the general form of the Langmuir equation has everything; it covers everything, but in different cases, you may have one or more of the terms not present, depending on the case in question. Right. So we would look at the general form for uh, a reversible reaction as depicted. So we would have the kinetic factor, the driving force term, and the absorption term. So there would be, if in certain cases you could have the absorption term being unity, as in high temperatures, you could have the absorption term to unity, so it's eliminated from the equation, right? Leaving you with this form. In a case where you have an irreversible reaction, right, or if the backward reaction is insignificant, then the second term in the driving force part of the expression goes away, leaving us with this form rather. And if it's still like in our first case where the absorption term goes to unity, then it simplifies further to this form. So we'll see. Most of the time when you see this expression or this kind of kinetics, it takes this form in general. Right? And rather than forward and backward constants, you have uh, the equilibrium constant present in there. And that can always be changed to suit the form Aspen takes. Right? As follows. So we go back to our problem. We see we have a rate law that takes a similar form and the pre-exponential factor. So we are going to try to specify this. We've converted the pre-exponential factor to its form. So we key that in here. Since it's a constant value, we neglect the other terms. That should be it for the kinetic term. And because we chose the Langmuir kinetics, we get two additional tabs here, right, to specify the driving force term and the absorption terms in our expression. So we could go there, and you see it gives us the option to specify the driving force term, and depending on the basis. In our case, is the partial pressure. So I'm going to choose that. So the key thing here is this is the term. If we come back here to compare this form of the equation to this, the driving force term in the parenthesis, the first part is term one. So that's what it's asking for. So if you have two terms, right, Right? Then you specify one for term 1 and term 2. And each one has a constant, the forward constant and the backward constant. And those are specified based on some coefficients, which we'll be looking at very soon. So if we go to our problem in a specific case, we do not have both terms present. Right? We have just one term, right? So in there we have toluene and hydrogen present and nothing else. So we go ahead, the exponent for toluene is 1, same for hydrogen. We do not have any of these out there, so you could alternatively you could leave it blank and Aspen will assume it's 0. So that is how it knows what is and what is not present in the form. Now when it comes to the driving force constants, that's the forward reaction and backward reaction constants. It's a bit complicated to specify. So Aspen takes these constants and uses them to estimate the constants, right, in this way. So this is the general form. It can also be linearized. Right? So they are also Arrhenius dependent. They have the form of the Arrhenius constant. Right? So hence the exponential terms in there. But usually it's going to be a value. I could modify this relation to suit a scenario if my constant resembles the Arrhenius form. Then just by specifying C as 0, I eliminate this T term. It becomes 1. I can specify D as 0 as well to eliminate this term, so that E exponent A computes my pre-exponential factor. And by specifying B, I could have the activation energy over gas, the molar gas constant term, right? In a case where it's a constant, I could eliminate this again by specifying C as 0. Do same for B as 0 because there's no temperature dependence, it's a constant value. Then I could also indicate D as 0 and just manipulate the value of A such that it gives me the whatever value of K I have or I wish to specify. So when we're looking at a specific case, we could see some examples here for the constants, right? And if my value is 1, for instance, then the terms in there, right? Assuming kf is 1, right? Then what I can do is I could indicate specify a value of 0 for all the constants. And when I do that, each one tends to 1, right? And that way, Aspen knows that the value of my forward constant is 1, right? If it's 10, right, I could take all of them to unity, right? I could specify 0 for D, 0 for C, 0 for B, right? And find the value of kf such that A is 10, right? Sorry, A. Find the value of A such that kf is 10. So in that case, if kf is 10, then ln of kf should give me A. So by specifying that value of A, my kf is calculated as 10, provided all these other coefficients are made 0, right? So going back to our problem, we do not have the backward term, we only have the forward term. It's the forward reaction. And the constant here, as you can see, is 1, because the K here is the kinetic factor. And so our forward reaction constant here has to be 1. The only way to indicate that is by specifying a value of 0 for all the coefficients. Then when it comes to the backward term, we need to tell Aspen it's not there first by indicating 0 for all the terms. And then we need to indicates that the backward constant is 0. If KB is 0, if the constant is 0, then we see the only way or the easiest way to achieve that is if B went to 0, C went to 0, D went to 0, right? Which will make all this term, the entire term here 1. Right? Then we'll only be left with EA. And in order to make KF 0 in this case, we would need to specify a large negative value for A, because the exponential function approaches 0 as the argument approaches negative infinity, right? So we could just do that by specifying a large negative value, and that should for A, and that should do. If we've done this, we can just go next. The next thing is our absorption term, right? And if we look here, it's the absorption term is usually expressed as a sum, and the terms in the summation are products of constants and concentration terms for the terms in the absorption. So we look here, this is a good example where the constants take this form, right? So if we compare this to the general form, right, then our first term here has the first constant, the K1. It's just the constants present. We don't have the concentration terms in there. The second term has a constant and a concentration term. So does the third. Right? So if these were our terms, our constants, then in similar fashion to what we did with the driving force term, since K1 is 1, then the length of K1 has to be 0. So the first value A, specify everything as 0, right? Then in the second case, we compare this. So once we linearize this part by taking the natural log, we get the values of these terms. And if you look back here, you remember that A is the first term and B over T is the second term. So once we apply that, we get a similar form. And we specify this value for A and this value for B, which we should be good to, right? So we are going to do the same thing for our problem. And so once you are here, the first thing it asks for is the expression, the exponent for your absorption term. And here, the exponent of this term is 1. Right? The entire absorption term is 1. So we specify that. And it now asks for the concentration terms. Right? So the first term is our 1. So this is the first term here. And do we have, whether you have any of these components in there, that's what determines what you put here. So since we don't have any of them in our first term, they all go to 0. Right. And then term number 2, we have benzene in there and nothing else. So every other thing goes to 0. And for the third term, actually, right. So we have that when it comes to the constants. So for the first term, term number 1, since this is 1 here, our constant assumes that value. That's constant assumes that value of 1. So the coefficient A, right, and remember when we went through the steps, this is how to indicate the value is 1 by setting all the terms to 0. When it comes to our second term, our KB, it's this value. And since it's just a constant value, 1 value, we plug this value into the log, the natural log function, and it gives us the value of A we should specify. And the same thing can be done for KT. So when we look back here, all that value was minus 11.204. And for our third term, which where we have Kate, it's minus. Right, and that should do it. Go back to our reactor. To the catalyst. Catalyst present. The loading was 10,000 kilograms according to the problem. Here we use a void of 50%. And once that is done, we should be cleared to run simulation. So we can quickly view our results. There's a heat duty. In order to keep our temperature at this point, we look at the profiles. Note that you can look for toluene and benzene. And we could look at our conversion. Toluene, about 80% conversion is attained. And if we come back to our profiles, we could see the kilowatts. And we could see the enthalpy flow or how the duty varies per length of the reactor. So that should bring us to the end of this lesson on linear Hinshelwood Haugen-Watson kinetics in Aspen Plus. There are problems in the reference material for practice. See you next time. Thank you.